All righty, good morning, everyone. So today we'll continue our discussion of forces. So life will be good. So last time, just to remind you, we started talking about forces. So primarily the most important thing for us right now is Newton's second law. So Newton's second law says that the sum of the forces acting on an object is then equal to its mass times its acceleration. So just to point out what I pointed out before, and we'll see a whole bunch of examples of this, the right-hand side is the easy part. So again, this is the how side, which is simply a yes or no question. So this says, is my object accelerating? Yes or no. If yes, I write MA. If no, I simply write 0. That's it. The left-hand side is where all the complication comes in, because this is a geometric representation of all the forces acting on the object, which means any force which is acting on it has to be visually represented on this diagram, which is what we call a free body diagram. And then we simply turn that diagram into a mathematical expression. So we look at the vector components along the different directions once we assign a coordinate system, and etc. So again, this is the part which changes from moment to moment. So basically meaning as I change the configuration of my system, the left-hand side is what changes, which causes the right-hand side to change as well. So again, the left-hand side is a geometric representation of all these forces, and the right-hand side is simply, again, a yes or no expression. So far, we've seen 3 different types of forces that we're going to run into a lot. The first one is the gravitational force, or the weight, which we've defined as F sub g, which is equal to mg, which again is mass times the acceleration due to gravity. And the direction of this guy, since g points straight down, that means the direction of this force is also straight down. So that's what this says. Direction is straight down. Second one is the normal force. We're going to denote that by little n with a vector sign. Direction of that, again, is perpendicular to a surface. So again, I have a normal force. I have to have 2 objects direct contact with each other. If they're not in direct contact, then there is no normal force. So for example, if this is my surface and my pen is above the surface, there is no normal force in this case because they're not in direct contact with each other. But as this thing then starts to sit on top of it, now there is a normal force. That normal force, again, is going to be perpendicular to the surface. Again, this is a reactionary force, which causes one thing to not move through another. And again, the last one is tension. So tension, we're going to denote by capital T with a vector sign. The direction of this then is along whatever the string is. So let me grab a cord here. So great, here's the power cord. So in this case, if I was hanging this mass off of here, the direction of the tension would be along the direction of the string. And again, we have some caveats with this. Again, here we are assuming that this has uniform mass distributed throughout the entire thing. So the tension at every location is exactly the same. We also are assuming it's massless. And then when it comes to pulleys, those guys are going to be frictionless and massless for now. But again, we're going to break those guys in the future. So good. Let's do a couple quick examples. And my first example, or at least my first question to you is, when I'm standing on top of the scale, so let's say I'm standing on my scale in my bathroom and I'm trying not to look at the number on my scale because I usually don't like what the number tells me, what does that number represent? So when I stand on top of my scale, so here's my bathroom scale and I'm standing on top of it, and I look down and I read a number, what does that number mean? So what is that number reading me? What is it telling me? What do you think? So which vector that we've seen so far, which force does my scale tell me?
Force of gravity, right?
Actually, no.
Or no, it's weight.
Well, force of gravity and weight are the same. That's fine. But the answer actually is no. In an ideal situation, the answer is yes. But what it actually tells me is my normal force. So when I'm looking at the scale, what it tells me is the amount of normal force the scale is pushing back on me versus my weight. Now, you're right. If I'm standing on it and there's no other forces acting on it, then in that case, the normal force is equal to the weight. So it does tell me my weight. But for example, if I was standing on my scale, right? So let's say here's my scale, and I grab the bottom of this table and I pull down, what happens to my weight? Well, it's going to go up because now what I'm doing is I'm applying an extra force downward, which means the amount the scale has to push against me is increasing because the normal force is increasing, which means my weight is going to go up. Or if I was standing on a scale and I push myself up on the table instead, now I'm applying an extra force upward, which means the normal force doesn't have to be as great, which means, okay. I think Bristen's in the wrong room. So tell Bristen he's in the wrong room. So he might be in the one that we were supposed to have yesterday. Okay. So what am I saying? Oh yeah. So if I push myself up, what'll happen in that case then is the normal force is going to go down. So what my scale actually tells me is it tells me my normal force. So what the scale tells me then is it tells me the normal force. So again, in an ideal situation, if I was just standing here, what would happen then is I would have gravity pulling down. So my weight, F sub g, down this way. But then I would also have my normal force pushing upward. So here's my normal force. And again, here we would say, well, the sum of the forces acting in the y direction are equal to 0. So let's call this our y direction. So in this case, I'd get my normal force minus my weight would be equal to 0. So in that case, my normal force would then be equal to the weight, right? So I said, so you're correct if I was standing on my scale with no other forces acting on me. In that case, my scale would tell me my weight because it's simply measuring my normal force. Well, what a scale actually does is it measures the normal force, doesn't actually measure your weight. And another way I can kind of convince you of that is our first example here is what would my scale tell me if I was riding in an elevator while trying to measure my weight? So let's say here I am in an elevator, and let's say this elevator is going to either accelerate up or down with a constant rate. So let's say the magnitude of my acceleration is simply equal to 1 meter per second squared. So if I was watching the scale, I want to know what would be my weight according to the scale, i.e. the normal force, if this thing is accelerating up or down. So we're going to actually do this both ways. So we're going to look at it while it's accelerating upward, and we're going to look at it while it's accelerating downward. So good. So in the first case, I have acceleration is going to go upwards. So I'm going to choose my positive y direction to be upward. So from here, we know that's what we're going to have gravity pulling us down. So we got the weight downward, and we'll also have our normal force pointing upward. So let's go ahead and draw our normal force. So here's my normal force. N. So good. So looking at the first case, I'm going to say, well, the sum of the forces in my y direction are equal to what? So is my elevator accelerating in the y direction? Yes, that was our assumption, right? So the right-hand side simply is going to become ma. Now let's look at the left-hand side. Since my elevator is what? Accelerating upward, and the positive y direction is upward. So the acceleration here has to be positive. Normal force is upward. The positive y direction is also upward. So that gives me a positive normal force. My weight is downward. Positive y is upward. So that gives me a minus mg then is equal to ma. So if I was looking at my scale then, I would then measure my normal force would be, add this term over here, my normal force then becomes the mass times the acceleration plus the acceleration due to gravity. This is what my weight would be according to my scale. So let's give you a concrete number. So let's say I weigh a mass of, oops, I want to use green because I'm going to use that here in a second. Let's use blue. Let's say my mass is equal to 107 kilograms. Okay. So if I plug that in to this expression, what I would find then is what? My normal force then would be equal to 1,155.6 newtons, which would then correspond to a mass, which would be equal to my normal force divided by the acceleration due to gravity, which would then be equal to, let's call this mass prime or apparent mass, would be equal to 118 kilograms. Okay. So what this means is if I was in an elevator accelerating upward at a very small acceleration of 1 meter per second squared, if I look down at my reading on my scale, it would tell me I now have a mass of 118 kilograms. This is what it would tell me, which means I had gained 11 kilograms by simply this thing accelerating upward. What would happen if it's accelerating downward instead? So if this thing was accelerating downward instead, so here I'm going to choose my positive y to be downward, and I want to do that to make sure that the y direction is in the same direction as the acceleration, because I have to remember that a here is a vector. So if this is in the opposite direction as my positive y, then I have to make sure I put that negative sign in here. So let's look at that one. So here I'd say the same thing. Some of the forces in the y direction are equal to ma because it is accelerating. Here, the weight is positive and the normal force is negative because the weight's in the same direction as my positive y, and my normal force here is negative because it's in the opposite direction. So I get an mg minus my normal force then is equal to ma. And then from here, my normal force then would be equal to what? M times g minus a. Plug in my numbers. In this case, I'd find my normal force would be 941.6 newtons, which corresponds to an apparent mass of now 96 kilograms. So in this case, I actually lost 11 kilograms. So in the first case, here we have a net gain of 11 kilograms, according to our normal force. And then here I have a net loss of 11 kilograms. Oh, good. So if I wanted to lose weight quickly by simply looking at the scale, what's the best way to do that? Go in an elevator that's accelerating downward. Better way would actually be go to the moon, but we'll talk about that later. So if I go to the moon, the acceleration due to gravity on the moon is roughly 1/3 of what it is here. So in that case, I'd lose a good amount of weight if I did that. So it was okay. Let's do another example. Let's do one with tension. So this example says that we have an elevator. Here's my elevator. And I'm going to accelerate that upward by pulling on the cable upward. So in this case, I'm going to pull upward with a tension. And the mass of the elevator is 10,000 kilograms. And I'm going to accelerate this guy upward with an acceleration of 5 meters per second squared. So what I want to know then is how much tension is being supplied by the cable. So how much tension does the cable have to pull this thing up at a rate of 5 meters per second squared? So good. So good. First thing we're going to do is, again, draw a free body diagram. So let's draw a free body diagram. So I'm just going to redraw it here just for funsies. Here's my mass. On here, we know we have a tension. That tension, again, is along the direction of the cable, which means our tension force is going to point upward. Gravitational force is always going to be downward. So we got Fg acting downward. And let's draw our acceleration. So even though the acceleration is not a force, I usually draw it on my free body diagram just so I know the direction at which it's accelerating. Okay. So you'll notice the acceleration I always draw off to the side, not actually on the object, because it's not technically a force. Okay. It's just the result of the forces. So good. So in this case, we know it's accelerating upward. So let's choose our positive y direction to go upward. So again, here we're simply going to write down Newton's second law. So Newton's second law says the sum of the forces in the y direction are equal to, again, the right-hand side is the simple yes or no question. We say, is this guy accelerating or not? In this case, is it accelerating? Yes. So this becomes simply ma. Good. So here, how many forces do I have in the y direction? So according to my picture, how many forces do I have in the y direction? I got 2. Good. So which one is positive and which one is negative?
Tension's positive.
Good. Tension is positive. So here I get a T. And what is gravity?
Negative.
Negative. Good. That one's negative because it's in the opposite direction of positive y. So good. So left-hand side simply becomes T minus F of G. And then all that's equal to ma. Good. Well, let's say is T minus mg is then equal to ma. So good. So here this says that the tension then is equal to the mass times the acceleration due to gravity plus the acceleration at which it is accelerating. So let's plug in our numbers. The tension then is going to be 10,000 kilograms times 9.8 plus 5. So this works out to be about 148,000 newtons. So this is my tension in the cable. It's okay. Not too bad so far, right?
I have a question regarding the previous problem.
The previous one, sure.
When you change the signs,
Mhm.
when it was going down, could you explain that again?
Sure. So I have to remember that when I write out Newton's second law, which says the sum of the forces as a vector is equal to the mass times the acceleration as a vector. Okay. So remember, the direction of the vector or the sign of the vector corresponds to how that vector points relative to an axis, right? So what's happening here is for the green one, since it was accelerating downward, I chose my positive y direction to be downward to make sure that this sign over here was positive. Right? But if I chose the regular one going upward, when in that case, let's say if I'm doing that, let's do that in yellow. When I wrote it out that way, if I did the sum of the forces in the y direction, I would have to be equal to mass times negative of the acceleration. If I chose the positive y to be this way, in that case, this side would look the same because the normal force would still be positive, mg would be negative according to this one, but I'd have to make sure I took that negative sign into account on the acceleration, because technically the acceleration would be negative because it's going downward with positive y is going upward. Okay. So typically what you'll see, what I do all the time is I'm always going to take a positive direction in the direction of the acceleration. And again, the reason for that is that way I don't forget about this negative sign. Because if I forget about that negative sign, everything's going to be all funky from there, right? So I'm going to get basically all the wrong answers. So one good habit to get into, and like I said, I'll do this all the time, is I'm always going to take a positive direction in the direction of the acceleration. That way I don't have to forget about that negative sign. Okay. Is that okay?
Thank you. Yeah.
You're welcome. All right. So next thing to talk about is Newton's third law. So yesterday, or 2 days ago now, well, we talked about the fact that if I was holding my cord and the cord was holding my keys, we said that here, since gravity is pulling downward, the tension of the cord must be pulling the keys upward. But simultaneously, my arm here is being pulled down by exactly that same amount of tension, but now being pulled down in this direction. Right? So the idea of this, and also the idea of me doing something simple like, for example, pushing my chair. So if I took my chair here and I push it, imagine I'm pushing a shopping cart. All of these things bring on what is known as Newton's third law. So what Newton's third law says is that for any force I apply to an object, that object applies the force back onto me with exactly the same amount of force at which I apply to it. So this is Newton's third law. So Newton's third law says that, again, if I was holding my keys here, or in this case, this cable, the amount that I'm pulling up here on the cable is the same amount as which the cable is pulling down on me. When I push this chair across the floor, the amount at which I push the chair in this direction is exactly the same at which the chair pushes back on me in this direction. Or if I had a nail here and I had a hammer and I did that, I apply a force to the nail by hitting it with a hammer, but simultaneously the nail applies a force to the hammer, pushing it in the opposite direction. These are all examples of third law. So the Newton's third law says for every force applied to an object by another object, that object applies a force back onto the first object. But then here, it also goes on to say that the forces are equal in magnitude, but opposite in direction. So this is Newton's third law. Other ways you probably heard this was that for every action, there is an equal and opposite reaction. This is another way of saying the third law. But basically all it means is that for every force that one object applies to something else, that something else applies a force back onto the original object with equal magnitude, just opposite in direction. Okay? So for example, if you were in a tug of war match with some other group, let's say your group's on this side and that group's on that side, and you're both pulling, the force that you apply to the rope is exactly the same amount of force that the other team applies to their rope. So actually the forces are exactly the same. One team wins as opposed to the other one, mostly because of traction and things like this. Okay? But this is what Newton's third law says. So basically for every force, there's an equal and opposite force. Okay? Mathematically, what that means is what? Let's say I have two objects. So here's object number one, let's say a person, and they're going to apply a force to object number two, this one. Okay? So this is object number one, this is object number two. Okay? So Newton's third law says is that the force on object one by object two is then equal to negative of the force on two by one. So the way that this is read is that this is the force on this object by this object. Okay? So this is the force on one by two is then equal to negative the force on two by one. Okay? So if I drew this, what this means is this is the force on one by two, and that's equal to the force on two by one. These two are just equal and opposite to each other. So all this means is that the magnitude of the force on one by two is equal to the magnitude of the force on two by one. Everybody's okay with this? So what that means again is what? If I was leaning against this board, the board is pushing on me in this direction with as much force as I'm pushing on the board in that direction. The magnitudes are the same, the directions are just opposites. Okay, so this is Newton's third law. Now, a consequence of Newton's third law is what happens if I have two objects which are connected to each other? Well, what happens is as long as those objects are connected to each other, what the third law basically does for us is it causes the two objects to accelerate at exactly the same rate. Okay, so what does that mean? So that means that, let's say I have something like this. Let's take an inclined plane. I'm going to put a pulley at the end, and I'm going to attach one object here via a string, let's call this mass 2, to another object which is on the plane, which is then mass m1. Okay. So let's say what I want to know then is what is the acceleration of object 1 here, and what is the acceleration of object 2? Okay. Now, what Newton's third law basically says is that what? This tension here is going to pull on this mass here to make sure it doesn't fall at the rate of g, but that tension simultaneously will pull onto this guy in this direction to make it force it to slide down the ramp faster than what it would want to slide. Now, what that says then is that the tension here by Newton's third law is exactly the same as the tension here, which means that the acceleration on the first block must then be exactly the same as the acceleration on the second block. Okay, so basically what Newton's third law tells me is that the acceleration a1 is equal to the acceleration a2, which is what we're just going to call a. Okay? This is what our most useful part of the third law tells us. That these two accelerations are identically the same. So good. So how do we solve a problem like this? So this is our next major thing we want to talk about. So we know the third law now tells me that this acceleration here is the same as this acceleration. So that means that if I want to find the acceleration of this guy, that's going to be the same as the acceleration on this guy. So let's say I want to know in this particular scenario, what is the acceleration of the system? So let's say, what is the acceleration of the system? So I talked about this when I talked about the keys. The way we handle problems like this is we isolate each object and we look at only the second law or Newton's second law when it comes to each object individually. So if I want to know the total acceleration of the system, I'm going to use the fact that this acceleration here is the same as this acceleration here, use the fact that this tension here is the same as this tension here, and then look at just the sum of the forces on this guy, the sum of the forces on this guy, and use those two things to solve these things simultaneously. Okay. So again, the way we deal with problems like this, things that are coupled to each other, is we look at the forces on each one individually, but then use the fact that here the accelerations are the same and the tensions are the same. So what's going to happen then most of the time is that the tension is simply going to be used as an intermediate to make sure that that gets related from this guy to this guy. So what the tension does then is it basically tells M1 that, hey, you're being pulled down in this direction because you're attached to M2. And then it's going to tell M2, well, hey, you can't fall at the rate of G because I got something up here, which is making sure that you don't fall fast enough. Okay. So what tells M1 about M2 is the tension. So M2 does not act directly onto M1. M1 does not act directly onto M2, but they act related to each other via this tension. Okay. So the tension is more like an intermediate. It's a way to transfer information from M1 to M2 and from M2 to M1. Okay. So let's look at this problem. So let's say what I want to know is what is the acceleration of the system? So let's do that. So again, the way we're going to do this is we're going to use and look at each object individually. So I'm going to draw a free body diagram for each one of these two objects. Okay. So from here, which one do you want to do first? Ruth, which guy do you like better? You like M1 better or M2?
M2.
M2, okay, good. So Ruth, give me a force on M2.
Gravity.
Gravity, good. Everybody's favorite. It's always the first one they always give me. Gravity acting straight down, good. Dane, I see you. So give me another force acting on M2.
Tension.
Tension, good. Which way is tension on M2?
Up.
Upward, good job. That's right. Good. We know this guy's going to accelerate downward. So is there any other forces acting on M2?
No.
What do you think? No, it's not touching the ground, so there's no normal force. There's nothing else we talked about. So these are the only two forces. Good. All right, so M1, who else is here? Preston, give me a force on M1.
Tension.
Tension, good. Which way is tension on M1?
Down to the right.
Good.
Diagonally.
Down the plane to the right. Good. So tension on that guy is going to be down in this direction. Good. Brooke, give me another force on M1.
The normal force?
A normal force, very good. And what direction is the normal force point?
Perpendicular to the plane.
That's right, perpendicular to the plane, so I was going to point off in this direction. So what color haven't I used yet? So let's use, I'm going to use red. There already is blue. No, I didn't. Good. So we make normal force blue. So it's going to go off in this direction. And Harrison, what's the last force on M1?
Gravity.
Gravity. Which way is gravity point?
Down.
Straight down. Good. So gravity is this way. So here, since I have two different gravitational forces, I'm going to call this one FG1. I'm going to call this one FG2. Okay. So good. Now, since each one of these two objects are different, that means I can choose a different coordinate system for each one. Okay. So what that means is whatever coordinate system I use for mass 2 doesn't have to be the same as the coordinate system I use for mass 1. Okay. And as I talked about in class, what I'm going to do is I'm going to use a regular traditional coordinate system on this one, but I'm going to use a tilted one on this one to ensure that all the acceleration is along one direction. Okay. So what that means is for this guy, I'm going to use positive y to go downward. For the same reason that Jair asked, is that what? I want to make sure the acceleration's in the same direction as a positive direction. That's why I'm going to choose this one to be downward. Here, keep skipping forward, I'm going to choose positive x to be in this direction, which is in the direction of the acceleration, which means that positive y must be this way. And if this plane is at an angle theta, then that means this is my angle theta here. So here, this angle here is the same angle here. So that's the angle relative between the y direction and the gravitational force. Okay. So good. So the way this is going to work is now I'm simply going to apply Newton's second law to both of these two different diagrams. Okay. So let's start off with M2. M2 is the easier one. Okay. So according to M2, we're just going to say, well, the sum of the forces in the y direction, is it accelerating in the y direction? Yes. Now here I have to be a little bit careful. Make sure you put a sub 2 on here because we're only talking about M2. So this is the mass M2 acceleration. Okay, so let's go back to our drawing here. So here we have two forces. We have gravity, well, force of gravity, and we also have the tension. Which one of those two is positive, according to our coordinate system?
Gravity.
Gravity, good. So here we have, let's write this out. This is going to be M2G minus my tension then is equal to M2A. Good. Now let's look at M1. M1, we now have two different directions. So we need to look at the sum of the forces in the X direction. And we also need to look at the sum of the forces in the Y direction. So let's look at each one individually. Let's see, who haven't I picked on yet? Ethan, which way you want to do first? You want to do X first or Y first?
Y first.
Y first, good. So Ethan, is it accelerating in the Y direction?
No.
No, good. So going to Y, we know the sum of the forces in the Y direction is equal to 0. And the reason for that is we chose our coordinate system, so all the acceleration was in the X direction. So in the Y direction, there is no acceleration. Good. Cole, give me a force in the Y direction.
In the Y direction?
In the Y direction
Gravity.
on this guy, yeah, on M1.
The force of gravity?
Good. Is it all of it or part of it?
Just part of it.
Part of it, and which parts?
Just, I guess it's just the theta part, or the theta part.
Good. So what I'm asking is
The
it cosine or
cosine.
sine? So remember that
The
here,
cosine.
this angle is here. So I'm looking at this piece. This is the adjacent side of this angle. So does adjacent go with sine or cosine?
Cosine.
Cosine, good. So it's cosine of the angle. And finally, one more question. Is it positive or negative? So positive Y is upward, and this
It'd be
guy's pointing
negative.
negative. Good. So pointing straight down. So good. So this is going to be a minus M1G times cosine of theta. Good. Very good, Cole. A lot of questions I had to ask you there. Sorry about that. So who haven't I picked on yet? Paige, let me pick on you now. So in the Y direction, what's the other force in the Y direction?
Force normal,
Normal. Good. All of it or part of it?
all of it,
Positive or negative?
positive,
Good. Plus normal force is equal to 0. Good. Good. Now let's look at the X direction. So let's see, who do I want to pick on now? Alexia, are you there? Maybe not. Okay. How about Gavin? Gavin, are you there?
Yeah.
Good. Okay. Gavin, is it accelerating in the X direction?
What, A? Or
Yeah. So is A pointing along the X direction?
yes.
Good. So here we simply get an M1A. Good. So for this guy, we get the sum of the forces in the X direction are equal to M1A. Good. Dalton, are you there?
Yep.
Good. So in the X direction, give me a force in the X direction according to this picture.
Tension.
Tension. Good. All of it or part of it?
All of it.
Positive or negative?
Positive.
Good. So here we get T. So here we have all of the tension acting in the X direction. Good. And that's positive. And the last force in the X direction. Let's see here. Jarrett, are you there?
Yep,
Good. So what's the last force in the X direction?
be part of the gravity.
Good. Is it positive or negative?
Positive. Well,
Very good.
it'd be
All right.
positive.
because it's pointing in this direction, same direction as plus. And if it was cosine before, then it has to be sine this time. Good.
Yep.
So I get a plus m1g sine of theta is equal to m1a. Good. Very good, Jarrett. So good. So now, once I got all of these expressions, now from here, the first one here, m2 in the x direction, says that I can find the acceleration of the system if I know the tension. Right, so this says if I know m2g, let's pretend I know m2. So here I can find the acceleration if I know the tension. Right now I don't know the tension. Where's the tension going to come from? Well, the tension is going to come from the forces in the x direction for m1. So basically here what I have are two equations. I have the sum of the forces in the y direction from m2 and the sum of the forces in the x direction from 1. And I have two unknowns. So from here, all I have to do is solve a system of two unknowns. However you want to do that is up to you. So one thing I could do is I can solve this one, for example, for the tension, plug that in here, and then solve for the acceleration. Or I can solve this one for the tension, plug it in here, solve for the acceleration. Or I can use the fact that this guy has a negative tension, this one has a positive tension. So if I add these two equations together, all that's going to happen then is that's what? The tension's going to drop out. Whichever way you want to do this is completely up to you. But right now, these are now just algebraic expressions, which are now just taken directly from our free body diagrams. So let me call this equation 1. Let me call this equation 2. And all I'm going to do is I'm going to take equation 1 and add that to equation 2. So let's do that. So now I get an m2g minus the tension is equal to m2a. And I'm going to add to that t plus m1g sine of theta is equal to m1a. So let's add these guys together. So if I do that, since this is a negative tension with a positive tension, those two tensions are going to cancel. Nothing else cancels. So in this case, I'm going to get an m2g plus m1g sine of theta is equal to m1 plus m2 times the acceleration.
I got a question.
Was that a question?
Yeah. I thought we had 3 equations.
Well, we do, but if I look at the third equation, does this have anything to do with tension or acceleration?
No.
No.
Okay.
So even though I have a third equation, for the most part, this is actually an unnecessary equation. So for all of you who told me forces in this direction, it was great practice, but it didn't actually do anything for us. Now, will it always be that case? The answer is going to be no. So the next type of force we're going to look at, actually, this will be essential. And that's what we call a friction force, okay? But for now, you're absolutely right, Preston. We actually have 3 equations, but this one doesn't give us any relevant information, at least as far as this problem is concerned. Very good. So from here, I've gotten rid of the tension. I've now gotten to the point where I can find the acceleration. So if I divide both sides by the m1 plus m2, this finally tells me then that the acceleration is equal to m2g plus m1g sine of theta, all divided by m1 plus m2. Good. And this is our acceleration. So let's kind of backtrack. So again, what we said was anytime we have things which are connected, Newton's third law assures to us that the acceleration of each one of these objects is the same. That the tension on this object here is the same as this tension, they're just in opposite directions. From there, to find the acceleration of the system, we isolate each object individually, look at all the forces acting on it, use the fact that this acceleration is the same as this acceleration, this tension is the same as this tension. And again, each one of these guys communicates information to the other one about each other via that tension. So here, even though we have tension in our expressions, that tension is only to tell M2 that M1 exists and to tell M1 that M2 exists. So basically what's always going to happen is that tension is going to cancel out. Now, does that mean I don't have to know what the tension is? Well, no. So if I was building something like this and I needed to have a cord that I had to have a certain amount of tension go in that cord and it couldn't exceed it, I would of course have to know what the tension would be in that cord to make sure that I had a strong enough material. But at least as far as these problems are concerned, I didn't have to know what the tension was. Good. So let's talk about the fourth force we're going to run into a lot. And that fourth force is what's called the friction force. So this is where that third equation is going to come into. Now, friction, what's friction? So friction is a type of what's called a retarding force, where a retarding force is a force which opposes the motion. So it's a retarding force which opposes the motion of an object. So what does that mean? So what that means is that the friction force will always be in the opposite direction of the motion of the object. Okay? So this means its direction will be opposites to the direction of motion. Okay. So what does that mean? So it means if my object's moving to the right, the friction force will be acting to the left. If my object's moving to the left, the friction force would then be to the right. So it's always in the opposite direction. This thing, the friction force is always parallel to a surface. So it's always parallel to a surface. So the normal force is perpendicular to a surface. The friction force will always be parallel to a surface. In general, I have two types of friction forces. The first one is what's known as a kinetic friction. And the second one is what's known as a static friction. So what does kinetic mean? So kinetic is the type of friction for an object which is moving. So this is the friction force, friction on a moving object. Static friction, what's static friction? So static friction is, so we have to be a little bit careful here. So it's a friction on an object which is not moving. Now, does that mean that the object doesn't really have to be moving? The answer to that is not really. So what it really means is that the object is not moving relative to the surface. Okay. So this is what this actually means. So to give you an example of that, as I walk, what causes me to walk? So what causes me to walk? What propels me forward? What do you think?
Just the friction of your shoes.
Friction on my shoes. What kind of friction? Is it kinetic friction or static friction?
Would there be both?
Depends on the circumstance. Most of the time it's going to be static friction, right? So when I walk, what I'm doing is I'm applying a force onto the floor that way, but the floor, by Newton's third law, is applying a force on me in this direction via the static friction. So I'm actually being propelled forward by the static friction by Newton's third law because I'm trying to push the rug or the floor this way, but simultaneously the floor is pushing me this way, which propels me forward. Now it would be kinetic friction if I was doing this, right? So if my foot was sliding out from underneath of me, I would have motion relative from the floor to my foot. So that would be kinetic friction. But in this case, it's static friction because my foot is not moving relative to the floor. Now you're right, if I was running on something like dirt, or if I was trying to run at very high speeds and my foot was sliding a little bit, in that case, it'd be a little bit of static and a little bit of kinetic friction. But most of the time I'm actually walking because of static friction. Same thing when you drive a car, right? When you turn a corner, it's actually static friction, which is pulling you through the center of the, towards the center of that corner, not kinetic friction. Kinetic friction would be as if your car was sliding through the corner. For example, if you were drifting or driving on ice, which is what we were doing the last couple of days. It's okay. So these are the difference. Now, kinetic friction, obviously the object is moving. So to determine the direction of this kinetic friction is easy. So my object's moving this way. Again, my kinetic friction is in the opposite direction. For static friction, since the object is not moving, what we really mean here is that the direction of the friction is opposite to the direction the object would be moving. Okay. So what does that mean? So that means if I took my cell phone and I put it on my hand and it was doing something like this, My object, in this case, my cell phone, wants to slide down this way, so the static friction must be pulling upward in this direction to keep it from sliding down my hand. Okay? So static friction is in the opposite direction of the direction of proposed motion, not the actual motion itself, because there is no motion. Okay? Now let's talk about each one of these two guys. What is the mathematical expression for each one? So each one of these guys are defined in terms of what's known as a coefficient of friction. So let's look at static friction first. So for static friction, we have to be a little bit careful because static friction, we're going to write F sub S, is going to be somewhere between 0 and a maximum amount. So this is static friction maximum, where that static friction maximum is equal to mu sub S times the normal force. So this is where that third equation comes from, because we'd have to find the normal force. So how do I know it can be 0? So for example, if I put my drink down here, so it was just sitting on the table, what is the amount of static friction acting on my bottle right now?
0.
0. Exactly. So in this case, it's 0 because there's no other force acting on it in the horizontal direction. So if my static friction was a maximum while this thing is simply sitting here, no other force would be opposing it. So my bottle would be accelerating across the table by Newton's second law. Because some of the forces says that's what the net force must be equal to mass times the acceleration. So if the only force acting on this would be the static friction, this guy would have to be accelerating across the table. That would be kind of cool. But that's not reality. Right? So that means if I have no other force acting on this object, there is no static friction because it's not necessary. So what this thing basically means is what? If I was applying a force onto this, and I looked at the static friction, if I have 0 force, I have 0 static friction. But as I start to apply more and more and more and more force onto it, the static friction must increase, 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 increase until eventually it reaches this maximum value. F sub S maximum. So that means as I'm pushing on my water bottle here, or my beverage bottle, if I put a little bit of force on it, the static friction is only a little bit. I put a little more force on it, the static friction becomes bigger. I put a little more force on it, the static friction becomes bigger. So it's in the opposite direction at which I'm pushing, where the magnitude is exactly equal to that of the force at which I'm pushing on it. Until eventually I push it hard enough that it starts moving across the table. In that case, I have broken static friction, so I have exceeded the limits. So we have to be careful with static friction. It's not always going to be maximum. It's not always going to be 0. Sometimes it'll be somewhere in this range. So to use this value, there has to be something in the problem which implies to us that it is at a maximum. If there's nothing that implies to us that it's at a maximum, we cannot simply use this. Okay? Let's talk about the coefficient. Coefficient, if this is a force, this is a force, this thing has to be dimensionless. So coefficients are dimensionless quantities. Dimensionless, I know how to spell, there you go. Dimensionless quantities. So it has no units. Okay. This thing is also determined by the type of material. Different types of materials will have different coefficients of friction. So if I was using, for example, I was pushing this on wood versus plastic versus ice, each one of these has a different coefficient of friction because it's dependent on the type of material. Now, what happens from there is if I keep pushing and this thing starts to move, this thing will eventually then kick over to kinetic friction. Once it kicks over to kinetic friction, it's then going to stay at a constant amount. So this constant amount here is what we call the kinetic friction. Kinetic friction is always a constant. This is simply equal to mu sub k, which is the coefficient of kinetic friction times the normal force. So this is kinetic friction. This guy is always going to be constant. Means as long as that thing is moving, no matter how hard I push onto my water bottle here, the kinetic friction will always be constant. Okay? It won't increase, it won't decrease. It will remain the same at all times. Okay? So this guy's constant regardless of external force.
I got a question.
Yeah.
So once it hits FS max on static, after it reaches FS max, that's when it starts moving. Like the object will
Once
start
it
moving.
exceeds that limit. So once it hits FS max, it'll still be stationary. But if I give it just a little bit more force than FS max, that's when it'll start moving. That's right. Okay, so once I just break that kinetic or that static friction, then it'll start moving with constant kinetic friction. That's right. So up to that point. So anything greater than that point, that's when it starts moving. That's right. Good. Very good. Same thing with mu sub k, just like mu sub s. Mu sub k is also dimensionless. It also depends on the type of material. And what's always going to be true is that mu sub s will always be greater than mu sub k. So static friction will always be greater than the kinetic friction coefficients. Everybody's doing okay? Now, the reason for static friction and kinetic friction is because of basically the material. So what happens is if I was looking at one material, no material is perfect, which means if I was looking at the microscopic version of the bottom of a material, whether it be this water bottle or this mug or my cell phone or whatever, this has imperfections to it. So this is what the actual bottom looks like. The table itself also has imperfections. So my table is going to do, I don't know, something like this. So basically what happens is because of these imperfections, what you're trying to do is basically push this object in its imperfections relative to this guy's imperfections. And what happens is that just creates a friction force. So I'm trying to scrape this guy past this guy, and you're getting all these what are known as contact forces. So this part is getting stuck on here. This part's going to get stuck in here. So as I try to move it across, this is what causes friction. So basically just the imperfections in these materials. So what we'll do on Monday then is basically just a whole bunch more example problems. Right? So be prepared on Monday. I'm going to call on each one of you individually to tell me forces, tell me directions, all the same stuff that we did today. So give me force in this direction, that direction. So we'll just work as many problems as we can basically on Monday. And then after that, we'll start talking about drag and then centripetal forces. Okay. So that'll be the last part of this class. Well, not of this class, but of this chapter, I should say. We got a little more to go in this class. So any questions so far? Everybody's doing okay? So as I said, be a little bit careful with static friction. Static friction is anywhere from 0 to that maximum value. So again, there has to be something in the problem which tells you it is a maximum. If there's nothing in there, you have to use the sum of the forces to then determine how much static friction force is actually acting onto it, whether it's 0 or somewhere in between that and maximum. Right? So again, if there's nothing that tells you it's maximum, do not assume that it's a maximum. Don't do it. Okay. Other than that, like I said, we'll do a whole bunch of examples. Monday, we'll do friction examples. We'll do all kinds of different stuff. Just get you better prepared on setting these up. But again, the game plan is always the same. You draw your free body diagram, draw your forces on there, put a coordinate system on there, apply Newton's second law. And then Newton's second law is nothing more than a visual representation of that free body diagram. So you're just copying directly from the free body diagram and putting it into a mathematical language. That's it. It's nice and easy. Okay. So if there's no questions, then everybody have a great weekend. And I will see everybody on Monday.
Have a good one.
You too. See you, Briston.
I have a question.
Sure, Jair.
Could you explain me electrical force?
Electrical force, that's a good question. That's something you'll see next semester. But basically what electric force is that any two objects which have a charge will feel a force between them. So basically what happens is if my, say, left hand is charged and my right hand is charged, these two guys are going to interact with each other because of the charge. Those two charges interact with each other. Now, the way that happens is, what's up?
And I was trying to do an example in the homework, and there was electrical charge, and it made the object to move a certain amount of degrees. Yeah.
All you need to know there is there's some force pushing in that direction. If it's an electric force or wind force or my son kicking it force, it doesn't quite matter that it's an electric force, just some force causing it to go in that direction. So that's,
So do I need anything or any?
no, you don't need to know anything about
equation?
electrical forces. No.
Okay. I think I'm a little bit ahead, but I have a question about drag force.
Sure, yeah.
There was a problem. I think I can read it for you. There was a problem related to drag